Okay, can everybody see me? Can everybody see me? Can everybody see me?
Yeah.
Okay, good. All right, good. I'm glad you can hear me too. All right, now, as I told the other students when I started with them and was trying to set this up, basically the test will include some questions on the gas laws regarding basically filling in the equations, and similar to the worksheet I passed out to you. Hopefully you were able to read ahead and work those problems and be able to figure out what the answer was. If you have any questions related to it, please come to my office, say after 12:15 to the lab time, and I'll be glad to go over any of it with you. Basically, what I'm going to do today is just finish off the chapter, the important parts, and then essentially end the semester. But I wanted to thank all of you for being attentive and everything and working hard. And I know it's been a struggle for many of you, but I struggle with my classes too, even chemistry. And it does pay off at the end. So all I can say is I'm thankful to God for the experience, as well as getting to know you, even though I can barely get to recognize some people because of the mask thing. So,
Dr. Douglas.
Yes.
What worksheet are you talking about? Like what?
I just sent out an email yesterday with the worksheet. Let me check.
I did not receive an email.
Second and or fourth test this week of reminders, but there's no attachment.
Oh, okay. Sorry. I'll send it out today. That big fine. You can work on those problems. My apologies. I noticed I just sent it to me. I didn't send it to the rest of the people. Annoying. Okay, I'll fix it. But basically, it's more useful for me to lecture on it anyway, so no harm done. But in any case, when you go through it this afternoon, just email me if you have any questions. I'm sending it right now, so you'll get it. So my apologies, I made it. It's all in my file. It just was sent to me, and I forgot to put the BCC in it. So in any case, that's covered there. Okay, so basically what we're going to do today is finish off the chapter and continue essentially where I left off on it. I do want you to get the big picture regarding the gas laws, but unfortunately with just two lectures, that doesn't really give it justice. But I encourage you over the break to read more on it, because some of it you will need for the next semester. Okay, so let's get going with this. I just sent out the message. My apologies for that, but it doesn't hurt anything for me to cover it first in class. Okay, now diffusion, effusion, Graham's law here, measurement of the pressure of gases, essentially with this. Okay. Let's start with this slide. And I'll be going relatively quickly through the slides here, just to get the big picture here regarding it, and then I will switch back to the other slides to fill out the thing. I'm going to share the screen with you now. Okay, now pressure is equal to force per unit area. Okay, and basically the pressure results the collisions of the gas molecules with the walls of the balloon that keeps the balloon inflated. Okay, now how can you provide pressure with your breath? Yeah, well that's more providing pressure with your lungs. Holding it will do it too. But pressure with your breath, you just blow out on something like a candle or whatever else, but you are providing pressure with your breath out, okay? You have pressure going in when you suck in, but it's related to that. But basically the pressure that comes from the collisions with the thing, if you blow on your hand, you'll feel the pressure, and that's all the gas molecules hitting the back of your hand, okay? So if you want to see it for yourself that way. Now, dry air consists of these gases primarily: nitrogen, oxygen, argon, carbon dioxide, and thing. And basically, carbon dioxide, just so you understand the nature of this 0.33, this is essentially, oops, let me go back. This is 330 parts per million. Okay, now notice it is 0.33%. And I do want you to understand about the nature of gases. The worst climate change people would say over the next 100 years that it will go from 330 ppm to 440 to 400 ppm and be really dangerous, okay? But in reality, what that is just going from 0 to there to 0.44%. Now, why don't they use the percent there to describe the issue regarding the 33% increase in carbon dioxide in the air? Why do they not use that? Why do they say it's 33% increase? Why do they use ppm, which no one knows really what they are? Why do people use that to kind of describe the nature of it instead of percent? Yes, okay, and that's the key thing. It is smaller because what's in the air also is a lot of water also, and particularly over oceans or whatever else, and water is a greenhouse gas too, much more than 0.44%. You go outside on a humid day, you can feel it, okay? So basically the key thing is science and critical thinking, particularly chemistry, will help you distinguish between propaganda and the truth. And another thing that's interesting too, do you know how much carbon dioxide was in, you've probably all seen Jurassic Park. In the Jurassic period, how much carbon dioxide was in the atmosphere at that point? Anybody know? 4%. That's a big difference, isn't it? Okay, that's huge. So yes, of course it's fluctuating. Whether man's involved or not, that's another matter. But basically that's what a lot of the debate is about. And I do want you to understand that the nature of our atmosphere is important. It's always in flux depending on sunspots and everything else. And so it's a situation where it's really important to understand the nature of the air we breathe and to distinguish the truth from kind of fiction. Now, pressure is exerted by a gas depends on the number of gas molecules present. Why? If you blow up a balloon with two breaths load into the balloon, and you put two more breaths in there, what's the pressure in the balloon is it gonna be better or smaller? If you're blowing up a balloon, you put two breaths in it. Okay, you then hold it. You then put two more in it. Is the pressure inside the balloon gonna be higher or lower? Higher, okay? And essentially it's related to the gas molecules. You just double the amount of gas molecules within it. The temperature of the gas. Now, when I was a kid, I would burn the trash. Very few people burn the trash these days, okay? Aerosol cans would get periodically in it. What would happen when an aerosol can was in it? It would blow up. Why? Yeah, because the gas inside was essentially heating up at such a point, the pressure got so hard, it burst the seams. So essentially it would blow up. And I always thought that was kind of cool, okay? Sure, it's dangerous, but the thing is at the time, because it was my job to do that, and it's important to understand the distinction between them. The volume in which the gas is confined. Now, if you have a balloon that's partially blown up and you squeeze it, what's the balloon gonna do when you squeeze it? You take a balloon that's partially blown up and you squeeze it in your hand. What's it gonna do? You squeeze it. it'll push back on you, okay? So essentially you're increasing the pressure in it by making the volume smaller by squeezing it. And you can do that for yourself sometime, particularly if you like popping bubble wrap. Basically, you will be putting pressure on it and then eventually it'll pop. But the point is, as you decrease the volume temporarily before it pops, the pressure will go up and that'll burst the seam. Okay, so basically there's a relationship between all those different factors. Now, atmospheres, this is that. The other book talked about atmospheres, the barometers. I already addressed barometers. Now, dependence of pressure on the number of molecules and the temperature. This is something that's very, very important. The pressure is produced by gas molecules colliding with the walls of the container. What's going to happen if you heat up the gas? They're going to move faster, so the collisions will be higher, so the pressure will go up. Okay? At a specific temperature and volume, the number of the collisions depends on the number of gas molecules present. Okay, so if you double the amount of gas molecules present at a specific temperature and volume, the pressure will go up in an equal fashion. Now, these basic observations are what people like Boyle and Gay-Lussac and Charles, all chemists or physicists, discovered when they discovered things. For an ideal gas, the number of collisions is directly proportional to the number of gas molecules present because of the fact that all the gas molecules act like the same under normal circumstances. And in reality, that is true. Okay? So basically, a specific temperature and volume, the number of collisions depend on the number of gas molecules. For an ideal gas, the number of collisions is directly proportional to the number of gas molecules present. Why? What's going to happen if you put four puffs into a balloon instead of two? What's going to happen to the number of collisions that occur inside that balloon? Much more, because you've got the double amount of there, but you also got them colliding with each other. So basically the collisions will increase based on the number of molecules. And then there's a little diagram there that kind of shows it. Okay, and basically the pressure exerted by the gas is directly proportional to the number of molecules present. Where you have the volume, 22.4 liters, the temperature is 0 degrees Celsius. The pressure of a gas at a fixed volume increases with increasing temperature. Okay, when the pressure of a gas increases, its kinetic energy increases because it's moving a lot. They're moving faster. And the increased kinetic energy results in more frequent energetic collisions. So basically, essentially, if you look at these two different things, notice inside the bottle, you've increased the temperature from 0 degrees up to 100 degrees Celsius, and the pressure in that bottle went up. That's just like the example I gave of blowing up a can in a thing, okay? The pressure of a gas is a fixed volume increases with increased temperature. The increased pressure is more frequent and more energetic collisions. Lower T, lower P. Now, Boyle is the guy that first came up with this relationship. And at constant temperature, the pressure, the volume of a fixed gas is inversely proportional to the pressure. In other words, you get that. Okay, so essentially you've got this, and basically that means that the PV, P times V, is equal to a constant. That is the nature of the situation. So if you're changing pressure or volume, you would have P1V1 equals P2V2. That is one of the formulas that you need to learn. So if this is an atmosphere, if you have 1 atmosphere pressure and 1 liter of volume, okay, what's going to happen to the volume if you go to 2 atmospheres? Okay, let's set it up. We're looking for the volume now for the second one. V2, you don't know what V2 is. So you just arrange it, P1 V1 over P2, like this, P1 V1 over P2 there. So basically you have 1 times 1 divided by 2, 1 times 1 divided by 2. So essentially it gets to be 0.5. Okay, so increasing the pressure will cause the volume to go down. Okay, and that's logical in those situations, that constant temperature. And the key thing is, this is one of the formulas that you just need to learn, okay? And Boyle essentially discovered this relationship between the things, okay? Your book kind of goes directly into PV equals nRT and kind of skips the background things, but it's very useful to help you where that all comes from, because I'll combine them all together and then you'll get the ideal gas law in a minute. But basically this relationship here. And basically Boyle graphed, he did experiments where he took different pressures and volumes and essentially showed the relationship between them. And basically as a scientist, he was able to do that. And an example is with a piston, the effect of pressure on the volume of a gas, essentially pushing down on it. And it's just like squeezing a piece of bubble wrap, the bubble on the bubble wrap. You're increasing the pressure as you decrease the volume. That's essentially what that's usually with a thing. Now, sample problem. An 8-liter sample of nitrogen is pressured at 500 torr. What must be the pressure to change the volume to 3 liters? What formula will we use? Good. P2V2. What is unknown? P2, good. So we take V2 there and we got it now, okay? So now we just put the volumes in. We have 500 torr here. You don't have to change units unless you want to. The volume is 8 liters. Then you take the other one, 3 liters down here. Liters cancel, you're left with torr, and you get the number. Very, very simple, straightforward problem. This is what's going to show up on the test tomorrow. Okay? A few of these questions. Yes?
So if it says like, what is the pressure or like a different pressure correct?
Yeah, but in this one, it just stays at torr.
Okay.
But basically, when you get the ideal gas law, then the constant is in atmospheres, so you have to switch it to atmospheres. And I appreciate you thinking ahead there, because we'll get to that in a minute. But the big thing is essentially you just set up the formula and then you do the math. Now, believe it or not, this is one reason many colleges and universities require college algebra first, because you practice the math first before you even see this. So basically what I'm doing here is teaching you some college algebra as well. So method A is conversion factors. You determine whether the volume is being increased or decreased. The initial final volume, the volume decreases, means the pressure increases. Step 2, you have multiply the original pressure by the ratio of volumes there. And basically you have that, and that's the PV equals nRT, like I showed you. Unfortunately, the words are there just so you can go through them in a step-by-step process, but I think you'd find it more useful to put it in that math form first. Yes? Yeah, it is. It's sorry. We did the same thing. Let me show you. It's PV1 V1 equals P2 V2, right? So you're trying to determine P2, correct? Okay, so essentially we have P2 now. This is P2, and this is the P1, and this is the V1, and then this is the this is the V2, the second one there. Okay. Yeah, that's things, but unfortunately they're using words to describe it in a different way. But you're gonna have the formula handy with you, and I use a combination of this, okay? Yes,
Why did it come out as liters?
well,
What is the conversion factor to get from liters to?
it's still liters. The liters cancel top and bottom. It's an 8-liter sample. What must be the pressure to change the volume to 3 liters? That's all.
What would we need a conversion factor?
Liters to they cancel out. It doesn't matter. Because a liter is like a quart. You can kind of thing there. Gases are usually in cubic meters, but liters are more appropriate for that. Does that make sense?
Dr. Douglas.
Yeah.
So torr, which is the metric used for pressure, correct?
Yeah, that's equal to
Yeah.
torr is equal to 1 millimeter of mercury.
I was just wondering, is 1 torr equal to
1 millimeter of
1,000
mercury.
liters? I know, but it's equal to 1,000 liters as well, because that's what.
No, it's a thing of pressure. 1 millimeter of mercury is the mercury thing. So 1 atmosphere is 760 millimeters of mercury, or 760 torr. It's just the unit.
So on the last one, why didn't they just keep it 13?
No, well, I'm saying, like, in the problem, it showed that when you multiplied it out, you got 1,333 liters, but then it went to 1.33 times 10 to the 1 torr. Yeah, there.
Well, they just put it in there as torr. What's the pressure there, and they just did the math. And you do the same thing. I just set it up without doing the math. They just did the math there because it changes into torr. That's all. So here you have these, the V1, 2, you set it up, the equation, you write it up with this, and I do it the algebraic way. If you want to do it the algebraic way, I think it's a lot easier to understand. There's 2 different ways to do that. And then you put the information in it and then calculate. That's what I did, Nick, right here. See? We
Yeah,
just
I did that.
do
I
the
did that
math
on
at
my
the end.
calculator. I did that on my calculator, but I get 1,333. So I'm asking, what, like, the conversion factor between torr and liter, I guess, because I don't get 1.3 times 10 to the 1.
This is the problem with these slides. The 1 should be a 3, okay?
Okay.
So they made a mistake somewhere. That's one reason I did the math and asked you to do the math, not worry about the answers given. Now the next one is Charles' law. And Charles, basically, he came up with the volume relationship with temperature. And basically what he found, it starts first with absolute value of 0, absolute 0 on the Kelvin scale. In a given volume of gas at 0 degrees Celsius is cooled by 1 degree Celsius. The volume of the gas decreases by that amount. So basically, if it changes there, so basically the 0 point is where all molecular motion stops. And what he found was a volume temperature relationship between volume and temperature. At constant pressure, the volume of a fixed mass is directly proportional to the absolute temperature. And that is equal to the V is proportional to T. So that equation becomes V1 over T1 equals V2 over T2, or V over T is equal to a constant, okay? And basically you're dividing both sides by T there. This is the constant there. So at the constant pressure, which is included in this constant, essentially the volume is related to the temperature.
What do you mean the constant? Like, what is the constant that you're measuring?
Well, it's just a constant relationship between volume and temperature. For example, if you have a balloon that has air in it and you heat up the balloon, what's going to happen the volume of the balloon.
The volume of the balloon's going to increase?
Yeah, that's it. That's essentially it, because it's all in atmospheric pressure. And you can try this for yourself. Blow up a balloon sometime, and put it in your oven at, say, 250 degrees Celsius. Sorry, 250 degrees Fahrenheit. Below the temperature, it would melt. So just put it in a 250-degree oven. If you let the balloon out, it will float to the ceiling. Why? Because essentially it's expanded. So essentially the volume is increased there, and then it displaces more air and it floats, okay? So the relationship there with Charles' law is the same thing as the other ones, essentially a relationship, and Dr. Charles came up with this relationship that V1 over T1 is equal to V2 over T2, okay? So that's another example of a problem you might work on. The effective temperature and the volume of the gas, the pressure is constant. When the temperature increases, the constant pressure, the volume of the gas increases. So that's the same thing what happens if you have steam in a steam kettle and you heat it up, that steam will cause it to whistle. Because the volume in the glass of the water boiling in there will increase, causing it to whistle. Okay, here, a 250 milliliter sample of nitrogen is at 75 is confined at a pressure of 3 atmospheres. If the pressure remains constant, what will be the volume of the temperature as it's increased? So basically conversion factors there, you got to convert it to Kelvin first. You got to remember to do that. 348. Those are the two numbers you're going to use. Multiply with the increase in volume. So now you have this. And again, they give the two methods. I like the algebraic one. Here, we have V1 over T1. And you have to change that. You put these values in there. This is V2. And then you put the information in there and calculate it. And basically that is the number, and the kelvins cancel. But the key thing is you have to convert Celsius to Kelvin. That must happen because we're talking about something from absolute zero. Okay, so this is what Charles came up with in Charles' law, the relationship between volume and temperature. And essentially that's what you can think with a hot air balloon. You increase the temperature in the balloon, it will rise and essentially go up into the sky because it displaces more air, so it will float. Now, Gay-Lussac's law, basically he found that pressure is directly proportional to the temperature. That's what I found with the can. Essentially, when you take the can, you heat it up in the fire at constant mass and constant volume, essentially the thing will pop. Yes. What? Sorry? Okay, now basically he found another relationship here. The pressure, this is the constant there. So P1 over T1 equals P2 over T2. And you got another sample problem there.
Dr. Douglas.
So let's try.
Will you
Yes,
go back? It was the P is equal to, what is the K?
that's the constant. This is a constant, okay? P over T is a constant at constant volume. The volume is included in this K.
So what's the value of K?
Well, in this, it doesn't matter because you're just comparing pressures and volumes with it, but it can be determined experimentally what that value is. Just by measuring a pressure and a temperature, you can calculate what K is, but it includes all some other things. Okay, But here with this problem, we have P1 over T1 equals P2 over T2. Let's set this up. If the temperature is raised to 100 degrees C, what will the pressure of the oxygen be? So basically you have P1 T2 divided by T1 equals P2. Okay, so what will P1 be? 2.15, okay? What will T2 be? Well, that's 373 Kelvin, okay? We switched it. So essentially I added that for you, okay? The T1 is 40 degrees higher, so that's 313 Kelvin. Kelvins cancel, okay? So this is in atmospheres now. So now that gives you the final number. So again, the two methods are saying this is just another sample problem. Yes? Because we cross multiplied. This goes up there. Remember, that's an algebraic thing. I'm teaching you a little math here, okay? I got a bachelor's in math. I love including the math in the thing when I have enough time to show people. That's why I keep asking you to come to my office and get help, because I love going over the problems with you. Okay. Conversion factors, again, you convert them with this. I'm going to delete this here. Do this, determine whether the temperature is being increased or decreased. The temperature increases there, plug in the values in. Step 2, you set it up that way. That gives the atmospheres there. Yes. I'm going to go over the other method. This method is just one of them gives you. And then the algebraic one. This is organizing it. Yes.
Why does it have P1 and 21.5?
Because that's an error too. Sorry. Yeah.
What's this equation called? 'Cause I don't see it on anywhere in our book.
No, it's fundamental to what's in the book. I'm going to get to what's in the book in a minute, because it comes from the PV equals nRT thing, and I'll show you how that works in a moment. Okay, I'm giving you the background for this. How many of you remember this from high school? Okay, well, that's the problem with teaching the test when you teach chemistry. This is why it's in Hein in an intro to chemistry class, is to go through this background here, okay? Because you understand it better. Yes. Sure, why not? It's one of the formulas.
I don't see it like the
P1 over T1 equals P2 over T2. Okay, that's what it is, but it is not in the textbook. It is foundational to the background. But basically, I'm teaching you this because I want to make sure you understand the nature of the relationships between them. Because this is the background of the ideal gas equation, and we don't have enough time for me to spend a week on the whole thing, okay? So I'm teaching you what you need to know. Most of you are biology majors anyway, so at least you'll get a basic understanding of it. Now, essentially, you write the thing there, you plug the values in, you put the numbers in there. Now you get the numbers, put them in there, 25.6 atmospheres. And again,
Wait, Dr. West, I thought this was 2.15. So it should be 2.56, right?
it's 21.5. He switched it. The error was in the top part. This is supposed to be 21.5, the way he filled it out, not the method I gave you. Okay, so essentially 21.5 there. See, he has 21.5. And again, the 21.5 is the thing there, okay? So write them out and then solve them in there as well. Now, each year I use the stock PowerPoint that I get with a textbook. So that's kind of what I'm stuck with. So there'll be small errors like this that I won't find when I go through them in preparation. So bear with me on those, but the math will turn out related to that too, okay? So you'll see the change will go from 21.5 up to 25.6. Standard temperature and pressure. The standard temperature and pressure, called STP, is at 1 atmospheres, which is 760 torr. And the combined gas laws, this is the combined one, where you have the thing PV equals over T equals a constant. And basically it will then combine with another gas law, which is Avogadro's law. Avogadro's law, which is essentially saying the pressure is directly related to the number of moles times a constant. The number of moles.
What is that constant?
Well, that's another constant. In other words, pressure divided by the number of moles, P1, N1 equals P2 divided by number N2. And that's the example I gave you before, where you have essentially, you put one breath into a balloon. The pressure, when you put 2 breaths, will be double the pressure with that, because you put 2 of it in there. Yes. No, Avogadro's is P equals, P1 over N1 equals P2 over N2. That's Avogadro's law. Okay, sorry, V1. It works with pressure too. V or P, either one. Avogadro's is officially volume over that. So basically, if I put 1 breath in, it'll be smaller than if I put 2 breaths in a balloon. So the pressure will double too. They work together.
Dr. Douglas, N is equal to moles, correct?
N is equal to the number of moles. And that's where I'm going to switch to the other book in a moment. But combining them, combining a Boyle's thing using pressure change at the same time, you have this equation here, where you have that, and you put there, you organize it with this. This is a sample problem at STP. If the pressure is increased to 950 and the temperature decrease, what will be the new volume? And it's just taking the formula and putting those in there too, and then essentially getting the values in it like that. And then it gives the algebraic method here, where you have those in there. Sorry?
Can you go back with one?
Yeah, this is P1 V1 over T1 equals P2 V2 over T2. That's the combined law.
Can you go back like the other one was like saying?
Here?
So I thought STP was, oh, never mind.
Standard temperature and pressure, yeah.
Because, okay, because like P is like 1 APM, but 764 equals 1 APM.
Yeah, and basically they're just using torr, the same units. It could be atmospheres, it could be torr. Doesn't matter. The units cancel.
Wait, so what is the standard temperature and pressure?
0 degrees Celsius and 1 atmosphere.
But that's not what was on the, so this,
I'm going back to show you.
so
0 degrees Celsius, 1 atmosphere.
So 271.15 kelvins.
Or 273, depending on 273.
So then which one would you like for the exam?
273. That's another small error in this slide. And as I said, these are little errors that I wouldn't find when I'm going through it. But see, minus 273, that's absolute zero, okay? It's standard temperature and pressure there. So basically, these are related to that. Now I'm going to go to the book and highlight the other parts just to show where we're going with this. But this is the combined gas law. And if you combine all of them together, Dalton's law of partial pressures, we don't have time for that one, but basically all that says is each gas will have its own pressure when it goes in. And the total pressure of the mixture of gases is the sum of the partial pressures of each one. Yes. Yes, of course. Yeah, they're on the worksheet I sent you.
Dr. Douglas.
But I encourage you to put those on your 3x5 card. Yes.
So the standard temperature and pressure, it's 0 degrees Kelvin, which is negative
No, 0
200.
degrees Celsius.
Okay, so 0 degrees Celsius, which is negative. Wait.
No, is 273.15 Kelvin. That's the standard temperature. The standard pressure is equal to 1 atmosphere.
But 1 atmosphere is also equal to 760 torr.
Yes, correct. Okay, so now essentially adding these things together. Now let me end the slideshow and go quickly to the other one. We've only got 10 minutes left.
So, the partial pressure isn't going to be on our test.
Sorry?
The partial pressure is not going to be on our test.
No. No. Hold on a sec. I gotta find it. I'm looking for the correct folder. Now I'm going to connect the two things with the thing now. I'm going to share this screen with you here. This is from our book. It's in chapter 10 of our book. Okay, here are the conversions. This is what the relationship between, for 1 atmosphere is 760. This is equal to torr. This is, the unit is the torr there, okay? The gas pressure to measure with this. The gas laws, 4 variables. Boyle's law, this is what I was illustrating. This is in the book here in chapter 2, okay? I took more slides with it. That's why the other one is better, okay? And then it shows another one there. So you have then the P1 V1 equals P2 V2. So that is one of the ones from our book, okay? Charles' law is the next one. Now these are just one slide, but I used 5 for each, okay? And gave you some sample problems. This is what the value of going to the other one too, okay? So basically you can see the relationship better. And then Avogadro's law, V is proportional to N there. And then basically, I don't know why they don't include Gay-Lussac, which is essentially equal to P1 over T1 equals P2 over T2. That's Gay-Lussac's law. And the ideal law then combines everything, and essentially it gets the PV equals nRT. Now, Brandon, you asked regarding what is the constant. When you have PV equals the constant, what is the constant there based on this ideal gas law equation? Brandon, can you answer that question? What's the constant?
Is it the N?
Yeah,
Or
it's
the
the whole
R?
thing. nRT, the K is the nRT. This is constant because the Boyle's law is at constant temperature, right? Then you have this R and then you have the number of moles.
So
So
what?
this is the constant. This is the constant you're dealing with, the constant.
The entire nRT is the constant.
Yes, correct.
So that means the pressure and volume will always equal the same thing.
Well, at constant temperature and pressure. No, at constant temperature. PV equals this at constant pressure. That's what Boyle's law says. At constant temperature. NR, the number of moles times the T. That, and then R is the other constant. This is the R. That's going to be given to you on the card, or you can write it on your card.
Wait, so what is L, ATM, and K mole?
Liters, atmospheres, K mole. Okay, so essentially you have the liters here, that's the volume, atmospheres, kelvins, and then moles. Okay, and then there's some sample problems. There's some samples there to do that, and the volume, for example, one mole of gas at STP is 22.41 liters.
Dr. Douglas, will you go back?
Yes, of course. But this is what the book uses, and I don't, are you Jordan? What's your name? Haley. This is what the book goes directly to, and unfortunately it doesn't give the background. So that's why I spent time giving you the background.
So what, Dr. Douglas, what is the value of N? That's just the number of moles?
Yeah, the number of moles, whatever number of moles of the gas you have.
Okay, and the R is 0.08206?
Yes. Okay, now stoichiometric relationship to this. For example, this is a stoichiometric question, plugging the values in there. We have the number of moles produced. Essentially, it's using stoichiometry, what you did before. We don't have enough time to cover that in the class, but this would be a sample problem of this type. But I do recommend you try some of these this evening, along with the worksheet that I give you. Yes.
Is the T in that equation the 0 degrees Kelvin?
In this equation, that's the T.
No, the NRT.
Yes, yeah. No, it would be 273 Kelvin. It's in Kelvin, see? It's in kelvins. Like at STP, this is kelvins.
And it's always, moles is always going to be 1 mole?
No, the question asks for 1 mole of gas. If it's 2 mole of gas, the volume would be double that.
Will the moles always be given? Or we have to figure the moles out?
Perhaps, unless you're asked a question related to changing the number of moles. Like in the next question here, which would be changing the number of moles when you have gases come off. Because this goes from a solid and gives off 3 moles of a gas, so that'll change it.
How would we figure that out, though?
What?
How would we figure out the number of moles if it's changed?
Well, based on the stoichiometric relationship here, if you have a certain number of grams, 45 grams of this, reacting to give this amount of moles of nitrogen, so basically you just plug the value of moles of nitrogen into that problem. And kinetic molecular theory of gases, I already talked about that. That's already talked about, and those other slides are better for that. And then diffusion and effusion and real gases, Van der Waals equation essentially is essentially there. So I did cover most of the chapter anyway, but now you know that our chapter basically uses PV equals nRT, and it just fills out the whole thing. Okay? Yes.
So where in chapter 10 are you gonna like stop and like if there's nothing on chapter, or you're just gonna put everything on?
Chapter 10, just read it carefully, understand where PV equals nRT comes from, and be able to do a problem if you're given any of those numbers to just do the algebra, just like the other ones. I give you the equation, and you just plug the values in. Just remember to change the things, and that's what you're going to see on the worksheet.
Okay, so like,
Just look at the worksheet. There's some examples on there.
so basically everything on the worksheet will be on the test.
No, similar questions to what's on the worksheet. And the problem, I work some more problems that are in Hind too, just as, so you understand, like I might have a Boyle's Law question or another one, but that's kind of hints at it in her book.
Yes, sir. I just didn't know where like you wanted to stop because you didn't get to everything.
Well, I got the 36 out of 40 slides on the slides that came with the book, so I sort of covered it, but I gave you a lot more background material today. And believe it or not, this chapter is what most students have is the most easy
Dr. Douglas,
because it's about the
Well-
math, and you folks are good at math. Yes.
what chapters from our book are on the exam?
Chapter 8 and 10, as well as some stuff from 7 that overlaps 8. Any other questions? Okay, we're done the slideshow and everything, so I'll be uploading everything, and we're done. Any questions? Those are still there.